Welcome to this explainer. If you've ever spent time trying to wrap your head around electrical engineering concepts, you already know that sometimes the theory can, well, throw you a massive curveball. Today, we're tackling a highly conceptual, honestly, kind of tricky interview question that stumps a lot of professionals. So let's just dive right into this and solve the mystery together. Picture this. You're sitting right across from a hiring manager. The pressure is totally on, and they hit you with this out of nowhere. Can neutral current ever be higher than phase current? Now, a quick heads up here. The interviewer isn't necessarily asking if you're going to see this every single day when you walk onto a job site. What they're really doing is putting you in the hot seat. They want to test your absolute fundamental understanding of electrical systems. Basically, they want to know if you can identify the exact conceptual conditions that would make this seemingly impossible scenario an actual reality. Now, to figure out how the neutral current could ever overtake the phase current, we kind of have to start with the baseline reality. We need to understand where neutral current actually comes from in the first place, right? You can't break the rules until you thoroughly understand them. So, let's take a look at how a standard electrical system operates under ideal conditions. Okay, so this right here brilliantly illustrates what we call a three-phase balanced electrical system. In this setup, we've got our three phases, R, Y, and B. Let's say the R phase is pulling 10 amps, the Y phase is at 9.8 amps, and the B phase is right there at 9.9 amps. As you can see, the current magnitudes are more or less exactly the same. Because of this harmony, the system is perfectly balanced. And what happens to the neutral current in a balanced system? Well, it's negligible. Actually, it's practically zero. But we don't live in a perfect world. What happens when things aren't balanced? In an unbalanced electrical system, there's a mismatch in the current flowing through those three phases. And when that mismatch occurs, the extra current doesn't just vanish into thin air. It needs a path to flow, and that path is the neutral wire. So whatever that unbalanced magnitude happens to be, it just flows directly through the neutral. Which brings us to a very logical conclusion. Even in an unbalanced system, the neutral wire is really just carrying the leftover, mismatched current. So, the absolute crucial point here is that under normal logic, the neutral current still shouldn't ever exceed the main phase current. It just doesn't make mathematical sense based on standard system behavior. Or does it? Section 1, the plot twist. Enter nonlinear loads. Okay, throw standard logic out the window for a second, because in a real industrial environment, the rules completely change. We are talking about nonlinear loads, specific pieces of technical equipment. We're looking at what I like to call the industrial suspects, things like uninterruptible power supplies, switch mode power supplies, and variable frequency drives. And I guarantee you, if you walk into any modern industrial workplace today, you are absolutely going to find these machines connected to the system 100% of the time. So we know these machines are literally everywhere. But what do they actually do behind the scenes? Like, why do they have the power to break our standard electrical rules and turn our neutral current into this surging powerhouse? Well, they trigger a very specific scientific mechanism that alters the very nature of the current flowing through the wires. And here it is. The true culprit behind this whole mystery is a phenomenon called third harmonics. When nonlinear loads operate on an electrical system, they actually act as sources that generate and produce these third harmonic currents. So this isn't your standard clean power flow anymore. No way. This is a severe distortion of the normal current. To really understand why this is such a massive aha moment, we have to contrast how standard currents behave versus how third harmonics behave. In a normal three-phase system, the currents in the different phases actually compensate for one another. They cancel each other out, which is exactly why the neutral current stays at zero in a balanced setup. But third harmonic currents, they're entirely different beasts. They do not cancel each other out. They don't compensate. Instead, they relentlessly stack and just keep adding up directly inside the neutral wire. So let's walk through this step by step so you can absolutely nail this explanation in your next interview. Step 1, your nonlinear loads, your VFDs, UPS, and SMPS, they're running on the system. Step 2, these machines inevitably generate those third harmonics. Step 3, because they don't cancel each other out, these third harmonic currents continuously add up and build upon one another inside the neutral wire. And finally, step 4, this continuous mathematical buildup pushes the neutral current so high that it physically exceeds the phase current. Boom, the impossible becomes possible. Section 2, industrial impact and essential solutions. Now, answering the interview question is fantastic, obviously, but we really need to connect this fascinating theoretical concept back to the reality of working on a practical day-to-day job site. I mean, what actually happens when you face this exact phenomenon in a massive industrial facility? Well, the real-world consequences are pretty significant. If you just let those third harmonics continuously build up the neutral current, it's going to cause absolute havoc and spawn a whole host of other major system issues. To stop this, industries have to install specific suppression filters and other protective gear. And that is exactly why, when you step onto a major industrial site, harmonic studies are straight up mandatory. Engineers have to meticulously study where these harmonics are generating and figure out how they can suppress them before they cause any catastrophic damage. So the next time you're looking at a complex electrical setup, you'll know for sure that the neutral wire isn't just some passive bystander. Under the right conditions, with enough nonlinear loads pumping out those third harmonics, it can literally become the heaviest lifter in the entire system. It kind of makes you wonder about the infrastructure right around you, doesn't it? Does your workplace run a purely balanced electrical system, or are there unbalanced conditions and nonlinear loads just hiding in plain sight, quietly building up those harmonics? Take a look around your site this week. You might be surprised by what you find.